Imagine gazing up at the night sky, not just seeing stars as they are now, but as they were billions of years ago. To witness the fiery birth of the very first galaxies, or the raw, untamed universe just moments after the Big Bang. This isn't a sci-fi fantasy, nor is it a trick of the light. It's the astounding reality of space telescopes, and how they quite literally allow us to see back in time. But how is this possible? How do human-made machines, orbiting far above us, achieve such an impossible feat? Today, on How It's Engineered, we're peeling back the layers. We're going to uncover the ingenious engineering and mind-bending physics that transform distant starlight into a window into the universe's past. Get ready to understand how light becomes a time machine, one incredible innovation at a time. At its core, the ability of space telescopes to look back in time relies on a fundamental principle of our universe, the finite speed of light. Light, astonishingly fast as it is, does not travel instantaneously. It moves at a constant speed, approximately 299,792 kilometers per second, or about 186,282 miles per second. That's fast enough to circle the Earth more than 7 times in a single second. But the universe is vast beyond human comprehension. The light we see from our own sun, just 150 million kilometers away, takes about 8 minutes to reach us. So when you look at the sun, you're actually seeing it as it was 8 minutes ago. The light from Alpha Centauri, our nearest star system, takes over 4 years to get here. So you see it as it was 4 years ago. Extend that logic to distant galaxies, some of which are billions of light years away, and the concept becomes profound. When a space telescope captures light from a galaxy 10 billion light years away, it's literally capturing light that began its journey 10 billion years ago. We are seeing that galaxy as it was when the universe was much, much younger. This is the ultimate form of cosmic archaeology, and light is our artifact. Now, why do we send these colossal, incredibly expensive telescopes into space? Why not just build bigger ones on Earth? The answer lies in 2 major obstacles that our planet's atmosphere presents: atmospheric distortion and absorption. First, distortion. Imagine trying to see a tiny, flickering candle flame from across a vast, turbulent swimming pool. The water's constant ripples and currents would make the flame blur and shimmer. Our atmosphere, with its ever-moving layers of air, heat, and pressure, does precisely that to incoming starlight. It blurs and distorts the faint signals, limiting the clarity and resolution of ground-based telescopes. This is called astronomical seeing. Even from the clearest mountaintops, the atmosphere smears starlight, making crisp, detailed images of distant objects incredibly challenging. Second, absorption. Our atmosphere acts like a protective shield, absorbing many crucial wavelengths of light, particularly ultraviolet, UV light, X-rays, gamma rays, and significant portions of the infrared IR spectrum. These wavelengths are vital because the earliest, most distant galaxies often emit light strongly in the ultraviolet, which then gets stretched into infrared by the expansion of the universe. If the atmosphere blocks these wavelengths, we simply can't, quote, see that ancient light. By putting telescopes above the atmosphere in the vacuum of space, they gain an unobstructed, crystal-clear view across the entire electromagnetic spectrum. So, how are these engineering marvels designed to capture such ancient, faint light? It starts with their incredible mirrors. Take the Hubble Space Telescope. Its primary mirror is 2.4 meters, 7.9 feet in diameter, polished to within a few nanometers of perfection. If it were scaled to the size of the Earth, the biggest bump would only be 6 inches high. This precision allows it to focus faint light with incredible accuracy. Then there's the James Webb Space Telescope, or JWST. Its primary mirror is a colossal 6.5 meters, 21 feet in diameter, but it's too big to launch as a single piece. So, engineers designed it as 18 hexagonal segments, each coated in a microscopically thin layer of gold to optimize infrared light reflection. These segments are engineered to unfold in space and then precisely align themselves to nanometer precision in a process that took months to achieve after launch. It's like building a perfect, giant optical instrument millions of miles away entirely by remote control. The larger the mirror, the more light it can collect, and the fainter and older the objects it can see. Complementing these mirrors are the detectors, the eyes of the telescope. These are incredibly sensitive scientific cameras designed to capture individual photons, the tiny particles of light, even after they've traveled for billions of years and are incredibly sparse. For infrared telescopes like JWST, these detectors must be cooled to incredibly low temperatures, just a few degrees above absolute zero. Why so cold? Because if the detectors themselves were warm, they would emit their own infrared radiation, overwhelming the faint signals from distant galaxies. It's like trying to listen for a whisper in a noisy room. You have to silence your own internal sounds. The location of these telescopes is also a triumph of engineering. Hubble orbits Earth in low Earth orbit, LEO, constantly circling our planet. This gives it a relatively clear view, though it still has to contend with some orbital challenges. The JWST, however, is located nearly 1.5 million kilometers, 1 million miles from Earth, at a gravitationally stable point called the Lagrange 2, L2 point. This remote location allows it to stay in line with Earth and the Sun while using a massive sunshield to passively cool its sensitive instruments, maintaining that crucial super cold operating temperature without constant power-intensive refrigeration. Beyond just collecting light, these telescopes are designed to see the invisible. While Hubble excels in visible and ultraviolet light, JWST is primarily an infrared telescope. This is key to seeing back in time because the universe is expanding. Light from the earliest stars and galaxies, which originally emitted in the visible and ultraviolet spectrum, gets stretched by this expansion, shifting towards longer infrared wavelengths, a phenomenon called redshift. By being optimized for infrared, JWST can pick up these ancient red-shifted signals, revealing parts of the early universe that were previously hidden. X-ray, gamma-ray, and radio telescopes offer other unique eyes, revealing energetic phenomena like black holes and cosmic rays. The challenge is immense. The light from these truly ancient objects isn't just red-shifted, it's also incredibly faint. After traveling for billions of years, only a minuscule number of photons from these distant sources actually reach the telescope's mirror. To compensate, space telescopes often need long exposure times, sometimes hours or even days, to collect enough of these sparse photons to form a clear image. This requires extraordinary pointing stability, precision, and isolation from even the slightest vibrations. So, how do space telescopes see back in time? It's a breathtaking symphony of human ingenuity. Colossal, perfectly polished mirrors to collect faint, ancient light, incredibly sensitive detectors, cooled to near absolute zero to register every photon, and precise orbital mechanics to position them in ideal, stable, and dark locations. It's engineering pushed to its absolute limits, transforming the very fabric of spacetime into a canvas of discovery. What other incredible feats of engineering do you want us to dissect? Let us know in the comments below. If you found this explanation of space telescopes enlightening, hit that like button and subscribe to How It's Engineered for more.